Imagine you're responsible for managing all the students in a busy school, keeping track of their grades, classes, and teachers. Or picture yourself handling every product in a massive online store, where thousands of items need to be tracked, updated, and found quickly. How would you organize all this information so you could find exactly what you need, right when you need it? You wouldn't just toss everything into one messy pile, you'd group similar things together, creating order out of chaos. For example, you'd have folders for students, teachers, and classes, each one holding related details. This is the core idea behind a relational database, organizing information into neat, related tables, each with its own purpose. Think of it as a set of spreadsheets that can talk to each other, each representing a different group but connected through relationships, making it easy to find connections between data. For example, a student table links to a class table, so you can see which students are enrolled in which classes. That class table, in turn, links to a teacher table, showing which teacher is responsible for each class. This structure lets us ask questions like, which students are taught by Mr. Smith? Or, what classes does a student have this semester? All without digging through chaos. Edgar F. Codd's revolutionary model, introduced in 1970, separates how we logically view data from how it's physically stored on computers. You don't need to know where the data lives on a hard drive, just how the tables relate and how to access the information you need. The Database Management System, or DBMS, takes care of all the technical details behind the scenes, so you can focus on your data and your questions. This logical organization is why relational databases remain powerful and popular even decades after their invention. They provide a structured, reliable way to handle vast amounts of information. Whether you're banking, booking a flight, or shopping online, relational databases are working behind the scenes. Every time you check your account balance or add an item to your cart, you're interacting with a relational database. Relational databases turn raw, scattered data into a clean, interconnected world of information, making our digital lives possible. At the heart of a relational database are tables. Think of them as grids, much like the spreadsheets you might use every day at work or school. These tables are the basic building blocks of how information is stored and organized in a database. Each table is designed to store information about a single type of entity, such as students, teachers, or courses, keeping related data grouped together for easy access and management. Columns in these tables represent attributes or characteristics, like student ID, first name, or date of birth. Each column is dedicated to holding a specific type of data, ensuring consistency across the table. Rows, on the other hand, are the actual records. Each row is a unique instance, such as one student's complete details, capturing all the information about that particular entity in a single line. No two rows are identical, thanks to unique identifiers, often called primary keys, which make sure every record can be found and referenced without confusion. This structure keeps data organized, consistent, and easy to update or retrieve, even as the database grows larger over time. For example, if you need a student's last name, you simply go to the students table, look under the last name column, and find the right row for that student. This makes searching for information quick and straightforward. The grid format is intuitive and easy for both humans and computers to understand, making it a universal way to organize data. This approach provides a solid foundation for building complex yet manageable data systems that can handle everything from small projects to massive enterprise solutions. That's the power of tables, rows, and columns in the relational model. They bring order, clarity, and efficiency to the world of data management. Keys are special identifiers that organize data and connect tables in a database. They help ensure that information is stored in a structured, logical way, making it easier to manage and retrieve data when needed. The primary key uniquely identifies each row, like a student ID for every student. It acts as a fingerprint for each record, making sure that every entry is distinct and can be referenced without confusion. No two rows share the same primary key, even if names or other details are identical. This prevents mix-ups and keeps records accurate, even in large databases with thousands of entries. Foreign keys create relationships between tables, acting as bridges that connect related information across different parts of the database. For example, An enrollments table uses a student ID as a foreign key to link to the students table. This connection allows you to see which students are enrolled in which courses. This ensures data stays consistent. No enrollments for students who don't exist. It helps prevent errors and keeps the database trustworthy. Secondary keys, or alternate keys, are unique columns that could serve as a primary key but weren't chosen. They provide additional ways to identify records. For instance, a unique email address in the students table could be a secondary key, offering another method to find or reference a student. Secondary keys offer alternative ways to find records, making searches faster and more flexible for users and administrators. These keys, primary, foreign, and secondary, are essential for organizing, connecting, and searching data efficiently. They form the backbone of relational databases. They maintain integrity and flexibility in the database, allowing it to grow and adapt as new information is added or updated. That's how relational databases keep everything connected and reliable, ensuring your data is always organized, accessible, and secure. For a database to be useful, its data must be accurate and consistent. Relational databases enforce integrity rules to prevent invalid or corrupt data. Entity integrity ensures every row's primary key is unique and never empty. Referential integrity means foreign keys must match existing primary keys or be null, no orphan records allowed. Domain integrity restricts column values to valid types and ranges, like only allowing positive numbers for age. These rules are enforced automatically by the database system. They keep data trustworthy, logical, and error-free. Integrity rules are the backbone of reliable databases. Without them, data would quickly become chaotic and unusable. Relational databases connect information without repeating it. Instead of storing customer details with every order, an orders table uses a customer ID to link to a single customer's table. This reduces redundancy. No more updating the same address in multiple places. Normalization is the process of designing databases to minimize duplication by splitting data into related tables. For example, students, classes, and enrollments are kept in separate tables, linked by IDs. Updates happen in one place and are reflected everywhere. This system keeps data accurate, saves space, and prevents conflicting information. Linked tables make managing large, complex datasets efficient and reliable. To retrieve and manipulate data, relational databases use operations from relational algebra. Select filters rows based on conditions, like finding students with a GPA above 3.5. Project picks specific columns, such as just first and last names. Union combines rows from two tables with the same structure, removing duplicates. Intersect finds rows present in both tables. Difference finds rows in one table but not the other. Join is the most powerful. It combines related data from different tables using common columns. Product creates all possible row combinations, but is rarely used alone. Divide handles for all queries, like students who took all science courses. These operations form the foundation of SQL, the language used to query databases. They let you ask complex questions and get precise answers from your data. Join brings related information from different tables together. Imagine a students table and a majors table. The students table has a major ID column that links to the majors table's primary key. To list each student's name and major, we join students and majors on major ID. The database matches each student's major ID to the correct major name. For example, Jane Doe's major ID points to history in the majors table. The result is a unified list of student names alongside their majors. Join lets you combine data dynamically, answering questions that span multiple tables. This flexibility is what makes relational databases so powerful for analysis. Without join, data would remain isolated and far less useful. Every relational database has a data dictionary, a special set of tables containing metadata, or data about the data. It stores details about tables, columns, keys, and relationships. The DBMS uses the data dictionary to check table structures, permissions, and data types before running queries. For administrators, it's a live blueprint of the database, showing how everything fits together. The data dictionary enforces integrity rules and validates changes automatically. It ensures all database rules are followed, maintaining consistency. Administrators rely on it for accurate, up-to-date documentation. The data dictionary is essential for managing and protecting the database's structure. Searching millions of rows would be slow without indexes. An index is like a book's back of the book index. It lets the database find data quickly. Indexes are built on columns and store values in sorted order, with pointers to the full rows. When you search for a value, the database checks the index instead of scanning every row. For example, an index on last names lets you instantly find all students named Smith. Indexes make queries much faster, especially in large tables. However, they slow down data changes, since indexes must be updated too. That's why indexes are used strategically, on columns often searched or joined. Proper indexing is key to database performance. It's a balance between speed and efficiency for both searching and updating data.